for examples of why do we need to do this. Okay. Just so happens I like car examples. You know. Sorry. So that's what we're doing on that one. So that's that. Like I said, you'll probably see some type of problems like that for homework, and then for quizzes or quiz for this chapter. This is just showing a glued wood joint. Now they do actually have a problem for that, I believe. 3 pieces of wood glued together to form an assembly, as shown there, can be used to test the shear strength of a glued joint. A load P of 50 kilonewtons is applied. Calculate the average shear stress in that joint, and note they're showing that the contact area is 75 millimeters by 100 millimeters. So then the area is 7,500 square millimeters, right? Assume the load P is equally resisted by each joint, and that the shear stress developed is uniformly distributed throughout the joint. Therefore, each joint resists 25 kilonewtons, 1/2 of the total load. The average shear stress is calculated as the 25 times 10 to the 3rd newtons, that takes care of the kilonewtons, divided by the area, which is 7.5 times 10 to the 3rd square millimeters. So then you got 3.33 newtons per square millimeter, or 3.33 megapascals. And that's probably how you're going to see most of the engineering data, is in megapascals. Okay? So simply just putting in the numbers and plug and chug. But they did change that, the 50 kilonewtons, they're saying each one of those 2 surfaces between those, between the middle piece, if you will, takes half of the load. You're having to assume that. In other words, the glued joint is exactly the same on both sides. Is that safe to assume? Not necessarily, but and it's wood, so you know the wood might break before the glue would break, potentially, probably more than likely. Okay, but again, if you're ever dealing with an engineered beam, you know, you could have some shear stresses involved on an engineered beam, and that would be where they would go and look to something like that. You know, you got your glued joint. That's exactly what's going on there, isn't it? So, something like that.
So 1 newton meter is equal to a megapascal, correct? I'm sorry, the newton per millimeter squared.
Is megapascals, yeah.
And then a pascal
would be 10 to the 6th. But
Pascal is a newton per meter squared, right? And mega is per millimeter squared.
I'll go with that. I don't remember. We just talked about that the other day, I think. It was in one of the example problems. But most of the time you're going to be dealing with megapascals. Yeah.
I'm not as familiar with the metric units.
Do what?
I'm just not familiar with the metric units.
Yeah, I wouldn't get too shook up about that. Okay. I tend to deal with the English units more than not. So, and you'll have access to all this if we do happen to throw one at you come test time. You got access to your book, so that shouldn't be a major issue. Okay. Well, let's see example 911. I don't think there's actually there isn't a picture for that one. It says a punching operation is being planned with a 3/4 inch diameter hole to be punched in aluminum plate 1/4 inch thick. Refer to figure 911. Where is 911? Oh, that's the one back. Yeah, that's that figure right there. Okay. In fact, why don't we just leave that right there for a minute? Let's see. For this aluminum alloy, the ultimate shear strength is 27,000 psi. Now they kind of threw something at you there. We haven't talked about the ultimate yet, have we? We should have, I guess. Did I? Oh, yeah, I kind of glossed over that, didn't I? Right here. Magnitude of shear stress achieved in the material when failure occurs is known as the ultimate shear strength. Okay, so when that thing breaks, that's you just passed the ultimate shear strength of that material. So when they talk about in that example problem, the ultimate shear strength is 27,000 psi, then you've got to get just past that, don't you? To make this thing, you're making it fail. Is exactly what you're doing. You're making the material that you're trying to punch fail. You're not making the punch that you're using to punch that hole with. You want to make sure that doesn't fail, right? So, but we're making sure that will fail. Let's see. Calculate the force P that must be applied to the punch. So what are we doing here? We're essentially sizing the capacity of the punch press, aren't we? And punch presses typically are capacity-wise, they're spec'd out as so many tons press. You know, they might have a 50-ton press or a 10-ton press. If you go to Harbor Freight and look at their punch presses, you know, their press apparatus, that's exactly how they're spec'd out, aren't they? 2-ton press or a 5-ton press. And that's how much force you can ultimately apply to whatever you're trying to punch. So with this problem, we're trying to figure out how much of that force are we going to need to get through that plate. And then, of course, you're also saying, well, I know I have to have at least more than that on my die to be able to punch that hole through. So I'm going to be putting that much on it, so I have to be much higher than that to make sure that die doesn't fail before the...
So it doesn't matter how sharp the edge of the die is? Like if you had a, like a ball pin die, even if you put that same pressure on it, it's going to go right through it just as it would if it had a...
Without getting into too much die design, absolutely. Okay. Yeah, that's where I said before on that bolted connection, if those two plates aren't close together, then it's going to be harder for that to shear. Okay, so because the farther away you get, and again, think in terms of well, and if you had a punch like a leather punch, and the hole on the bottom was much bigger than the die, then you're basically drawing that material down into it before you make it fail. Then it's a matter of, do I have enough room to draw that down into that hole before it shears? If it doesn't, then you're just doing what's called a drawing operation, and you're making like an aluminum cup.
Yeah.
It would be what you would be doing. You'd be stretching that material down through that opening. It's very similar to doing an extrusion, but you're pushing the extrusion through with your die. So that's a drawing operation.
Is that real bad for material or no?
Well, it depends. I mean, if you're trying to make it fail, it's just failing the operation. If you're trying to punch the hole through and you're actually drawing it, then you're not getting the job done. That wouldn't necessarily be bad for the material, but it changes the material's molecular makeup because you're stretching that material. So in some cases, it will actually make it stronger. Okay, so from that standpoint. So what else do we have here? Assume the shearing stress is uniformly distributed. We're going to assume that on everything. I don't know why they keep saying that. Resisting shear area is the circumference of the punch multiplied by the thickness of the plate. So they did give us enough information. It's a 3/4 inch diameter hole, and the plate thickness is 1/4. So we multiply the diameter times pi times the thickness. Then the resulting area, which is kind of interesting, the resulting area is 0.589 square inches. How's that work? Why is it square inches? Why wouldn't it be cubic, right? But what you got to think about is it's just what you're looking at as far as the area is concerned. And if I can find my pen on my screen. That was interesting. Anybody see my pen? Oh, there it is. If I could just get the... what's making that move. Okay, now there's my pen. There it is. Come on. Okay, so what you're looking at there is, you're looking at this area right here, aren't you? You're looking at the circumference of that blank. That's the area you're overcoming, all the way around that diameter. So that's why it's pi d times the thickness. And that's why they can get by saying it's a square inches as opposed to a cubic. So you're not dealing with, and maybe I can do it better from this mouse. You're not dealing with a volume there. You're just dealing with that thin veil around the diameter of that plug. Okay? Pi d times the thickness. And that's the area. So then it's a matter of what do we have? The ultimate shear strength is 27,000 psi. So what you're trying to find is P, aren't you? So you're given the average shear stress. I'm going to have to go back to my OneNote. Let's see the next class because I can't find it. You're given the shear stress, the average. I gotta find it. It's like having my hands cut off. Okay, it should be right there. We go. You're given this value right here, 27,000 psi, right? You're given this right here, and you're looking for that right there in that problem. So ultimately your answer should be in this case, it is English units, so ultimately your answer should be in pounds. So you were given, so you'd have to rearrange this equation. You're looking for P, and you've got the area. Can't believe that an electronic pen would run out of ink, can you? And now I've lost it again. Okay, make note of this. This will be the last time I use PowerPoint. That's an A, and that's tau. God. I don't know why it's going away. But that's, so you find your area, which we did. That was pi times the diameter times the thickness, 0.589. We multiply that by 27,000. We end up with 15,900 pounds of pressure that it would take. You would have to hit that punch to get down into that material and break it, essentially, or make it fail. Shear. Okay. Well, let's see. Back here now. Now this one, we're dealing with a little something different. So I think it goes back to what Anthony had asked back here.